Right, we are starting off with sets of numbers, and so we're going to start off with a definition of what we mean by a set of numbers. So what is a set? A set's a well-defined collection of objects which are called elements. So the elements are the objects inside of a set. And what do we mean by well-defined? Basically, it says that it has to be clear as far as whether it is in the set or not in the set. So for example, if we were talking about the set of vowels that are in the word textbook. So if we had the word textbook and I said my set includes all the vowels in the word textbook, there can't be any debate as far as whether something is in the set or not in the set. So in the word textbook, we would include E as an element in that set, and we would include 0 as an element in that set. We wouldn't include any of the other letters because it's clear that they are not vowels. So as far as describing our sets, there are some different ways that we can do it. There's the verbal method, kind of like I just said. I mentioned the set of all vowels in the word textbook. That would be a verbal way of describing it. There's the roster method where we use these braces, a left brace and a right brace, and we put the elements in there only once. Even though in our word textbook we had the O in there represented twice, if I were to list that set, I would include the E and I would include the O, but I need only list that O once in my set, even though it is, twice in the word. So each element is only represented once. That's the roster method. That's a pretty popular one. Set builder we're going to do quite a bit with, and it is actually a combination of both that verbal description and our roster, and it uses the variable x. So we're going to do that with most of our numeric representations. Okay, so sets of numbers. These are some very popular sets that we're going to be dealing with throughout this text. The first one being the empty set. An empty set is appropriately named. It is a set that does not have anything in it. The symbol there, which kind of looks like a 0 with a line through it, is one way of writing it. Another way is to use these empty brackets that don't have anything in it. And another way, this is our set builder notation. The way that you would read this is you would say the set of all x's such that x is not equal to x. So again, that's all x's such that x is not equal to x. Think of a number that could be in our set that was not equal to itself. And we would have no elements. So that's the empty set. And then we have natural numbers. Natural numbers commonly referred to as our counting numbers. Numbers like 1, 2, 3, 4, 5, 6, etc. They go on and on and on. So these are all natural. And then if we include one element, if we add the element 0 to those natural numbers, then we now have whole numbers. So it goes from 0, 1, 2, 3, 4, 5, and on and on. And then if we included negative numbers, so we've still got our integer, we've still got our natural numbers, we've still got 0, but now we also have -1, -2, I believe that is -3, and on in the opposite direction. We now have all of our integers. So far, no fractions, no decimals. These are our whole numbers and their negative or opposites. But then we get to rational numbers. rational numbers we're representing here with our q. Rational numbers can be written as fractions. They can be written as fractions where a is an integer and b is also an integer. So both the numerator and the denominator of our fraction are integers. It is very important that the denominator is not 0, because thou shalt not divide by 0. Just quickly, the way that we would read this, we would say that q is the set of all fractions, a over b, such that a is an element of z, which z is of course all integers, and b, the denominator, is also an element of z, which is all integers. Okay, so another way of describing these rational numbers is to say that that q is the set of all elements x, such that x possesses a repeating or a terminating decimal representation. So anything that we can write as a fraction, we could either say is a terminating decimal, or it could be a repeating decimal. So for example, 2/3 is 0.6 repeating. That's a rational number. Or 3/4 is 0.75, which is a terminating decimal. And by the way, all of those integers are also rational numbers, because any of them, like the number 3, I can write it as a fraction, 3/1. So I can write any of those integers as itself over 1, so that makes it rational. Now I'm going to skip real for just a second and skip down to the irrational. So irrational numbers are numbers that are, as the word may imply, not rational, not rational, but they are still real numbers. So think of a number that cannot be written as a repeating decimal or a terminating decimal, and the numbers get perhaps a little bit stranger, but numbers like pi. Pi does not repeat and it does not end, but also numbers like the square root of 2. The square root of 2 is irrational because it cannot be written as a fraction of integers, and it doesn't repeat and it doesn't terminate. So whenever you put the rational and irrational numbers together, that is the set of real numbers. Real numbers, all x's such that x possesses a decimal representation. Does it terminate? I don't know. Does it not terminate? Does it repeat? If you put together our rational and irrational numbers, you have the set of all real numbers. And then lastly, we have complex numbers. Complex numbers have the form a plus bi, where a and b are both real numbers, and I is the square root of -1. So, very important field here, but as you can see, we're not going to go into that in very much detail in this series.